I've got a function f, and it's a mapping from the set x to the set y. And I also, let's just say for the sake of argument, let's say that f is invertible. F is invertible. What I want to know is, what does this imply about this equation right here? The equation f of x is equal to y. I want to know that for every y that's a member of our codomain, so for every y, so let me write this down. For every y that's a member of my codomain, is there a unique, I'll write it in caps, unique solution x that's a member of our domain such that, and I could write such that, well, I'll just write it out. I was going to write it the mathy way, but I think it's nicer to write it in the actual word sometimes, such that f of x is equal to y. So if we just, let me just draw everything out a little bit. We have our set x right here. This is x. We have our codomain y here. We know that f, if you take some point here, let's call that a, it's a member of x, and you will apply the function f to it, it'll map you to some element in set y. So that's f of a right there. This is so far what just this tells us. Now, I want to look at this equation here, and I want to know that if I can pick any y in this set, or any lowercase y in this set y, so let's say I pick something here, let's say that's b. I want to know, is there a unique solution to the equation f of x is equal to b? Is there a unique solution? So one, I guess you have to think, is there a solution? So is there a solution is saying, look, is there some x here that if I apply the transformation f to it, that I get there? And I also want to know, is it unique? For example, if this is the only one, then it's unique, but it's not unique if there's some other guy, if there's more than one solution. If there's some other guy in x that if I apply the transformation, I also go to b. This would make it non-unique. Not unique. Yeah, not unique. So what I want to concern ourselves with in this video is, somehow is invertibility related to the idea of a unique solution to this for any y in our codomain. So let's just work through our definitions of invertibility and see if we can get anywhere constructive. So by definition, f is invertible implies that there exists this little backward-looking, 3-looking thing. This means there exists. I think it's nice to be exposed sometimes to the mathy notation. So let me just write there. There exists. That means that there exists some function. That means that there exists some function. Let's call it f inverse. F inverse. That's a mapping from y to x. From y to x. Such that. And actually the colons are also the shorthand for such that, but I'll write it out. Such that the composition of f inverse with f is equal to the identity on x. So essentially it's saying, look, if I apply f to something in x, and then I apply f inverse to that, I'm going to get back to that point, which is essentially equivalent, or it isn't just essentially equivalent, it is equivalent to just applying the identity function. So that's ix. So you just get what you put into it, such that this inverse function, the composition of the inverse with the function is equal to the identity function, and that the composition of the function with the inverse function is equal to the identity function on y. So if you start in y, and you apply the inverse, and then you apply the function to that, you're going to end up back in y at that same point, and that's equivalent to just applying the identity function. So this is what invertibility tells me. This is how I defined invertibility in the last video. Now, we're concerned with this equation up here. We're concerned with the equation, I'll write it in pink, f of x is equal to y. And when we want to know for any y in our, or any lowercase cursive y in our big set y, is there a unique x solution to this? So what we can do is we know that f is invertible. I told you that from the get-go. So given that f is invertible, we know that there is this f inverse function. We know that there's this f inverse function, and I can apply that f inverse function. It's a mapping from